Silicon Graphics has created an environment in which high-performance computing is applied to visualize information. Everything in the universe is defined by its form and flow. Being able to examine the structure of any complex system helps us comprehend its function, process, and relationships. Whether it's a building or the building blocks of life, once we see how the components of a structure interrelate and we come to a fundamental understanding, we can, in turn, create more effectively. Silicon Graphics provides computing power and visualization technology to people who are at the leading edge in their field. Today, Silicon Graphics systems are being used to work on some of the most challenging problems and to create some of the most complex applications. The Silicon Graphics visual computing environment allows people to understand complex structures by literally viewing the information which defines those structures. The creation of software is an extraordinarily complex task. It is concept, imagination, and information translated into a textural form. The process of building applications is similar to the building of any complex structure. There's a multitude of components, layer upon layer of construction, with work distributed among a team of collaborators. Today's software can contain millions of lines of code, linked together into a single system of interacting components. Previously, developers had no means of visualizing the structure and flow of their software. Silicon Graphics CASEVision is the only integrated software development environment that helps you manage complex development problems through visualization. To developers, one picture is worth 1,000 lines of code. CASEVision adds an order of magnitude to that picture. Running on any SGI workstation, such as this Indie Dev Station, CASEVision is the optimal tool for the development of next-generation software. CASEVision's elegant user interface displays rich information that is faster and easier to analyze than text. The CASEVision product line includes CASEVision Workshop for debugging, testing, and performance tuning. CASEVision Tracker, which is a dynamically customizable change control and change tracking application builder. CASEVision ClearCase provides version control and configuration management tools for Unix development teams. The CASEVision Workshop Suite includes the Static Analyzer, a visual system for programmers to navigate through and analyze the structure of their code. The Static Analyzer provides programmers with the ability to view call trees and the relationships between callers and callees, which is clearly referenced by arcs. For C++, the Static Analyzer displays the class hierarchy of the code and supports queries. The Static Analyzer provides a clear view of the dependencies among files and allows instant access to source code. CVD, the Workshop Debugger, is a leap beyond standard debuggers. Created from the ground up with advanced underlying technology, CVD's multiple-level graphic views are dynamically updated during program execution. CVD includes tools such as GL Debug and the Array Visualizer, which provides both a table and 3D graphic view of large arrays to detect and locate anomalies quickly. The Workshop Debugger provides other time-saving functions like fast data watch points and direct access to machine-level debugging with a graphical approach to memory and register information. CVD provides a multi-level view of many aspects, but still allows programmers command line DBX when needed and direct access to any source code. The CASEVision Workshop Build Analyzer allows launch and access to the compilation and version control processes from within the workshop environment. Compilation errors are displayed, and source code is readily accessible for modification at any time. The Workshop Performance Analyzer provides information on CPU utilization, memory leaks, paging, resource usage, heap corruption, and other problems. Another key feature of CASEVision is the intuitive graphic interface and seamless integration between tool sets, including third-party modules. CASEVision is an entire family of products that are designed to be integrated via ToolTalk, with additional modules available from third parties, such as Teamwork from Cadre. CASEVision and Indy, like all SGI products, incorporate Unix SVR4 standards, 64-bit RISC, and 3D graphics as core technologies. The Indy platform incorporates these technologies in an extremely powerful and affordable workstation. Software developed on an Indy has 100% binary compatibility with the entire spectrum of SGI hardware, including hardware with symmetric multiprocessing. In the video that follows, we'll be showing more details on these products. The CASEVision Workshop Core Toolset and CASEVision modules. Modules include Pro MPF, Pro C++, CASEVision Testing Tools, CASEVision Tracker, and finally, CASEVision ClearCase. We invite you now to join us for the comprehensive series of demos which follow.
Hi, my name is Michelle Chambers, and I am the product manager for the CASEVision Workshop line of tools over here at Silicon Graphics. CASEVision Workshop is a complete programming environment that includes debugging, performance tuning, and static analysis. It's really the low-level performance or programming environment that you need for any C, C++, or Fortran application. I'm going to give you a quick demo of our debugging environment and some of the performance tuning tools, and then I'm going to hand it over to Anil Paul, who's a member of the technical staff here at Silicon Graphics. Anil is going to go into a more in-depth performance tuning experiment, and then he's going to cover some of the new modules that we've just released here at Silicon Graphics. Those would be the workshop line of tools that we call our professional series, and it includes a higher level debugging environment for C and C++, as well as a new native compiler for C++, tools for doing multi-process Fortran application development, and some software testing tools that we've just come out with. So let's take a look at the workshop tools. First thing we have up here on the screen is the workshop debugger. And you'll note that this is a source level debugger. It handles C, C++, and Fortran applications. And over here in the top, I'm going to bring up my little Jello window, and I'm going to leave it up here. It's going to run. And one of the things to note about our debugger is that it's not just a motif window over DBX. What we actually have done here is completely re-architected the debugging environment. And we have a number of views that we can look at in our program that makes this environment extremely unique. So the first thing I'm going to do is stop my process, and I'm going to bring up one of these views. The first one I'll bring up is the structure browser. And I can type in any expression into this line. So we'll say Jello Connect, and take a look here at a linked list. I'm going to open this window a little bit wider, and I can double click on any pointer in here, and it'll automatically dereference that pointer for me. Now I happen to know that I'm looking at a linked list in here. It'll take me quite a while to go out and double click on these if I want to look at the whole list. So I'll bring up an overview window for you. And then I'm going to go into my formatting menu and say, let's dereference all future instances of this pointer. And I've also told it to stop after it does 5. And we can look up here in our overview window now. We can see where we initially started and look at the additional pointers that we dereferenced in here. I can also go in, this is extremely configurable, look at values in a number of different ways, octal, hex, floats, char strings, look at their bit size, look at their types. Very configurable tool. I can iconify these windows. I can make it extremely configurable to my preferences. Next tool we're going to look at is the array browser. And this is a great tool for going in and looking at extremely large arrays. Type in the name of an array in here, and you'll notice that we have a two-dimensional array. Make this a little bit bigger. This is shown to us in a spreadsheet format. So I can go in here and move through my spreadsheet. You can see the numbers come up, the array values come up in the window here. I can step through the array very easily if I want to. I can change my stepping notations. I can also move through the array very easily by moving the subscript controls around. I can also look at it in a column row or row column format. Now what I'm going to do, makes this a little bit more interesting, is go out and actually get a rendered picture of this array. So it's going to show the array values to me in a 3D format. And what I'm actually going to be looking at here is a two-dimensional plane of the array, looking at it in 3D. Let's hue ramp this a little bit. And I'm going to make this window bigger. So we really need to size this guy up. Now I can go in here and modify this a little bit, zoom in on my array, which is what I'm actually looking at. That's what this blue line is here. And I can move the array around. And you'll notice here that we have an extra on in here. And you notice that there's also an anomaly in the array. I can see from this spike that there's some problem in the array at that point. So I can take my little joystick sort of thing here and actually move to that point in the array. And then I go down to my spreadsheet where I've highlighted that point on the array, and I notice that the value I have in there at that point is 1,000. If I look at the other values in the array, I can see that that's clearly out of line. Also, if I go in and I look at the pattern of the array, I can see that I have a number of zeros following through here, and that this array value probably should be set to 0. So I have definitely an error that's happening there. So I can go in, modify that array value to 0, and as I've made that modification, I can now look at this and see that the spike has indeed cleared. So this is one way that Silicon Graphics has applied visualization to the software development process and made it much easier to handle extremely large amounts of data in the development cycle and be able to look at that data clearly and solve problems faster. Now I'm going to go into general features of the debuggers. Those are some of the highlights, but let's bring up a couple of windows here. I'm going to bring up my call stack. I'm going to need to use a little bit more of the screen here, and I'm also going to bring up my trap manager. One of the nice things about the trap manager in general, let me point this out to you, is that I can go into my program and set a number of breakpoints in the code. And the trap manager will show those to me, and I can actually just turn them off right there and go ahead and say continue. So if I have a number of breakpoints set in the program, it's very easy for me to go in and start and stop the program just by setting the breakpoints and clearing them through the trap manager. I don't have to go in and comment out my code. I can also go into the trap manager and set conditionals and things like that. We actually have a bug in Jello that I'm going to make hit right now. I'm going to go in and set our display to grow. And when I do that, we can look up here in the status box of the debugger, and it will tell us that we've stopped on signal sig bus error. And it tells us we were in the function draw shadow at that point. If I pop up my call stack, I can now look on here, and if I move down the stack, go into draw floor, I can then see that I was actually referencing surface triangles at the point where that happened. So now I'm going to go into the static analyzer and see if I can find anything from there. And I can launch any of my workshop tools from the main debugger window. Actually, I can launch any of my workshop tools from any other tool. So it's very easy for me to move right into the static analyzer from there. And what I'm going to do with this is bring up my queries menu and say, let's list all the functions in the program. And now I'm going to go in and highlight surface triangles. And as I do that, it automatically pops up into the static analyzer query target. Now I'll bring up my view, and we'll bring up a call tree view of this. And from the call tree view, I can bring up an overview window that'll let me easily move through the display. So what I want to do here is go in and look at surface triangles, and I'll do a query on that variable. And let's say who set surface triangles. Well, it shows me here that 2 functions set that. Well, let's say I want to look at this within the context of everything that's defined in my program. I can specify that as well, and then I can easily move in my overview window down to the point where those functions are located in my program. Now I can go ahead and double-click on either of these functions, and it will automatically bring up the source code for me relevant to that, and it will also highlight in that source code not only the function that I was in, but where the variable surface triangles was set at that point. So I can see that we are set at surface triangles equal to triangle. That looks fine. Let's move up in here to reset Jello. I can double-click on reset Jello. It takes me to that function. I move down to the location in the code where surface triangles is set, and I can see it's set to null. That looks fine. So it doesn't look like there's anything wrong with surface triangles. So let's go in now and set a watch point in the program. At this point, I'm going to go in and bring up my trap manager. First thing I'll do is kill off Jello up here. And now I'll go in and run Jello again. Start this whole process up over. And we can see Jello and Jello spinning. Now I go to my trap manager, and I can put in a watch point at my trap line. So we'll type into here, watch surface triangles. Oops, to stop the process first, that would help. Say watch surface triangles, the watch point is set. Now we'll say continue. Jello's still running, and you'll note that the watch point performance here is extremely fast. That's one of the things that Silicon Graphics has architected into the CASEVision Workshop products, is the ability to have extremely fast watch points. We've done this through kernel support in the debugger. So now let's go in and make the bug hit again. I'll go back to display, say grow, and if we look in here, we can see that we are stopped on the watch point writing this particular address. And it points me to the area in the code where the watch point actually hit. And I can see that we've notated in here that we actually do have a dangling pointer that we need to get rid of. So let's go ahead and do that. Now I'm going to go up and go in and say, let's check out this file. Okay, so now I've checked out the file, and what I need to do at this point is go in and remove this line. So I'll do that, delete the line, save that, and now I'll go in and recompile. And we can see that the compile took off automatically. Now it's attaching to the rebuilt executable. And at this point I can go back in and rerun Jello. And we'll set him spinning, set the display to grow, and in fact it does work. Okay, at this point I've brought up the debugger again, and from this point I can go in and launch my performance experiments. So the first thing I'm going to do, I have a new executable in here, it's called malloc-bug. The first thing that I'm going to do is go in and load up the performance experiments. So let's take a look at how we do this. What I'll do is bring up from the admin menu the performance task panel. And within the performance task panel, and Anil's going to go into this more later, but from here I have a number of different types of things that I can choose to do for performance tuning. I can determine bottlenecks, look at CPU time per function, source line, or ideal time. What we'll do in this case is find a memory leak. So I can select Find Memory Leaks. It will automatically bring up the correct experiment directory for me and let me do a malloc free trace, and that's what's been highlighted in here. So we'll go in and say OK, and now I will run my instrumented executable. I can watch my progress for this in my execution view, which is up here, see the state that I'm in. I can also watch the status in my status box, and I can see that this is already run. It's very quick. So now I'll go into my admin menu and I'll launch my performance analyzer tool. What I've done in this process is I have linked to a specific malloc library. So I'm able to go in and bring up performance tuning information. And it allows me to go in and look at the memory leaks within the program and also any bad frees. The Performance Analyzer tool allows me to go in and visualize this. So what we'll take a look at now is the heap view. So from here I bring up heap view, and it gives me a graphical display of what's going on in my dynamic memory. This is actually a display of the heap, and if you look down here in the search box, I can hold my button down and I can go over the entire map here, and it will bring up all the memory locations for me. If you look up here at the top, I can notice that all my mallocs would be in red, and those would be any mallocs that were made that were not freed. Reallocs would be in a navy blue, green would be indicative of a free, and my bad frees come up in this sort of a cyan color. So what I'm interested in first actually are my bad frees. Let's take a look at one of these. I'll select one. We go down here to the bottom and it shows me the bad free address, and it also shows me the associated call stack. At this point I can double click on that stack frame and it will bring up the source code for me, and it brings me directly to the location where the bad free was made. So if I go in and look at this code, I can see that I char-starred C here, I char-starred D at that point, and I have 2 frees of C, so I incorrectly freed C at this point. We also have performance statistic annotations on the side of the source view. Let's go back up to the heap view, and notice if I double click on one of the red lines, again it gives me the malloc address, the associated call stack, and I can double click on that stack frame and it will bring me to the location where I made the malloc.
Hello, I'm Anil Pal. I'm a member of technical staff in the Software Development Environments group at Silicon Graphics. What I'm going to show you is the performance tools component of the workshop tools product that Michelle showed you earlier, the debugger. One of the things about performance tools is that modern programs tend to have more performance problems than simply CPU usage. I/O, paging, and graphics are important components of the program. The other thing is that interactive programs and programs with graphical user interfaces tend to run for quite a while, and there are different phases of the program that require tuning differently. So the performance tools are designed to address this, but they have something called the sampling paradigm, where you can sample the different phases of your program and narrow in on the parts of your program that are of interest to you so that you can tune the different phases differently. For example, you may have some parts of your program that are I/O bound and other parts that are CPU bound, and you need to tune them differently. Okay, if we come over on the screen here, what I've done is I've run a performance analysis experiment on a program with the default performance experiment, which is to determine the bottlenecks and identify the phases of the program. Down here, I have a timeline of the execution of the program with sample points at regular intervals during the program. This graph here shows resource usage by the program and what state it was in at various points. The color key here shows us that there are times when the program is running in user mode, running in system mode, running in graphics mode. It could be waiting for I/O, waiting for raw I/O, waiting for memory, waiting in select, and all the different states that a program can be in. If we look at this graph over the time of the program, we note that there are three readily identifiable phases that spring out at us. This first section here, the program is running in system mode. Then there's a section here where the program is waiting for raw I/O or paging. And then finally, there's an extensive section where the program is running in user mode. So let's try to take a closer look at this and find out what really is happening in these three phases. So what I'll do is I'll bring up a more detailed graphical usage view of the program and look at that. Now, as I scroll down here, I notice there are lots of graphs in addition to the system state that are collected here. I have a count of the page faults of the program, the context switches, the bytes read and written, the read and write system calls, and the other system calls, as well as the total size of the program. Now, by relating these, I look at the number of read calls, the kilobytes read and written, and relate that back to the initial time, and I notice that that initial system time was all spent in reading data. So I've identified the first phase of my program as being a read phase. The second phase, when the system is waiting for I/O or paging, I note corresponds to a lot of page faults on the graph here. So I can say that that second phase is a period during which my program was paging. And that's the second phase. And finally, the last phase of the program is when it's actually doing the calculations. So now I'm ready to look at these three phases individually and tune the program for each of those three phases separately. So let me go back to that now. I'll go back to the main view of the program, and I'll move these calipers here on the timeline. I'll close them in to select just the initial phase of the program, that is the part during which it is reading. When I hit OK on that, if you come up to the top here, I'll see a list of the functions in my program sorted by the amount of time that they spend in that function. And I'll notice that one of the top functions here is one called getArray. So if I double click on getArray, I'll now bring up the source code annotated with the performance data over that section of the program that I was looking at. And I'll see here in the right-hand side on the scroll bar, there are some points marked of interest. And those are the parts of the program that have high execution counts. So if I look down at the bottom, a lot of time was spent in the call to get array, which I knew. And as I go up into get array, there's one particular line here which says if f read, and that's where all the time was spent that's highlighted. So I know now that this read statement is the statement in my program that is consuming all that time in the initial phase of the program when I was reading data. So I can look at that and see if there's any way I can tune it, and perhaps I can improve the performance of that. Right, on to phase 2 of the program. In this case, I move my calipers again now to select the second phase of the program, during which there was all the paging activity. So I set the calipers to expand that phase of the program. I hit OK again. And now when I bring it down, you'll see the list of functions has sum1 as the major function. So that indicates to me that this is the function that's doing the paging. Once again, I can double-click on that to bring up the actual source code. And when I get the source code and look at it, I'll have the line identified here where all the time was spent. And when I scroll down to that line, I'll see, let me expand this window a little bit so that you can see that I'm actually accessing an array in 2 different ways. And what I'm doing is I'm accessing the array very inefficiently, which is causing a lot of paging. So I can adjust my array accesses, perhaps rearrange the loop so that I step through the array in a more structured fashion and reduce the paging and get rid of that phase of my program where I'm thrashing the memory. So that's the second phase of the program. Now we're left with the final phase, which is the actual calculations where the program is using the CPU time. So let's go back and take a look at that. I move my calipers now for this last phase of the program where there's only CPU time being used. I hit OK for that. And now I get a function sum2 is the main function that's using all the time. I can double-click on that, bring up the source code, and I will actually get line by line the amount of time spent on each line in my program. If you look down here, the lines that are highlighted are the call to sum2 and the actual line in sum2 where I'm doing some calculations that shows me the heavy usage of CPU time during this phase of the program. So that then is, in a nutshell, the performance tools. I was able to look at the entire run of my program, identify the separate phases, determine the behavior in each of those phases, and then zero in on each phase separately and tune that particular phase so that the overall performance of my program is optimized. Hello, this is Anil again. I'm now going to show you CASEVision Tester, which is a test coverage analysis tool. What it lets you do is see how effectively your test suites cover the code in your program. This lets you modify your test suites so that they test the maximum portion of your code without redundantly exercising the same portions over and over again. What you do is you run your test suites, and CASEVision Tester will instrument the executables while you run the test suites, and then graphically show you which parts of your code were and were not covered by the tests. So let's take a look at the screen here where I have Workshop Tester running. And what I do is I type in the name of a test experiment that I have previously run, and I can then ask a bunch of queries about that test run. I'll start with listing a summary of the test, and what that will show me is for each of the types of coverage that Tester measures, that is function coverage, it says I've covered 2 out of 2 or 100% of my functions in my program. For source lines, I've covered 17 out of 35 or about half. And the branches are highlighted because 0 out of 10. This means every time my program branched, I've always gone the same way in my tests. I've never gone the other way. And that's a concern because it means I'm not testing the other cases in my program. So let me look at this a little more closely. So I go in and say list branches, and I get a list of the branches in the program. I can now double click on any of these, And what I will get is the source code view of my program, where I can now see what is it in the source code that was not being tested by the branches. And looking at this, you can see it was all the error conditions in my program. So if I had too few arguments, if I had too many arguments, or if some command returned a bad status, all of those cases were not tested. Basically, I was only testing the straight through case in the program where everything worked. And that's a very weak test suite. I do need to test all the exceptional cases. Luckily, I've thought of that, so I have another set of tests that covers those cases. And let me go and switch to that now. So up here, if I type in the name of this test set, and tester will allow you to have either individual tests or sets of tests, I can now query and list a summary for this test set, which is several tests that I have. And you'll see for this test set, my coverages are much closer to 100%. 2 out of 2 functions, 35 out of 35 source lines, but there's still only 9 out of 10 branches. And I can see this more clearly if I take a bar graph view. You'll see that the graphical view, the branches are not fully covered. So let me investigate that more closely. I say list of branches, and now I get a list of the branches with the one branch that I didn't take highlighted in red. So once again, I double click on that to bring up the source code. And when the source code comes up, I can see there's no lines highlighted because, as I had before, all of the lines in my code were covered. So let me take a more detailed look by looking at the disassembled source code of my program. And this will look at the actual assembly language instructions. And here I can see the lines that were not covered. If I relate these back to the switch statement here, what I'll see is that what I'm not testing is the default case in my switch. If you look at this switch statement, there are 3 cases, but there's no default case. Now what's happened is that my test didn't test for the case of falling through in the default case. So in this case, by revealing the shortcoming in my tests, I'm actually finding a bug in my program that I was not testing for. So I can modify my test suite to actually test for this default case, and I'll find whether or not there is a bug in my program in that case. So to summarize, tester allows you to look at the test coverage of your program, design better test sets, and those better test sets will then help you find bugs in your program before your customers find them. Hello, I'm going to show you Workshop Pro MPF, which is a visual interface to our Parallel Fortran Analyzer tool to help you develop Parallel Fortran applications. What PFA, or the Parallel Fortran Analyzer, does is it will take regular Fortran source code and parallelize it. Certain parts of code cannot be parallelized, or the user may wish to direct the parallelization. What Workshop Pro MPF does is provide an easy interface for you to find out why pieces of code cannot be parallelized and to direct the analyzer as to how to parallelize them, thereby letting you get the maximum performance from your code. Let's take a look now at the screen where we see a piece of code that has been analyzed, and what you see here at the top is a list of all the loops in the program. Along with each loop on the left is an icon showing what the status of that loop was. I'll bring up a key which will tell you what those icons mean. There are loops that could not be parallelized, loops that were parallelized, and serial loops that may be merged with a parallel loop or were optimized away. Okay? So if I look through this, I can then double click on any one of these loops, and down here at the bottom it will tell me what was done with that loop. At the bottom of the screen here it says what the messages were. For example, for this loop it says that the loop was unrolled 4 times to improve scalar performance, and a cleanup loop for loop unrolling was added. I can go to the next loop and get the similar messages saying there was too little parallelizable code, but the loop was unrolled. The transformations that can be done are fairly complex. If I go down to the end here and look at one that's actually a matrix multiplication program, you'll see there was many things that were done to this loop. It was loop unrolled 4 times, there was a cleanup loop, a do loop was inserted, and the strip mining block loop was inserted in order to maximize the cache performance of the program. To show you this, let me bring up the original source code for this program, which here shows what it really is a triply nested matrix multiply that you can zoom in on here. And what I can then look at the transformed source code that PFA produced from that, and we'll see that the code has greatly expanded because of this expansion of the loops in order to maximize the cache performance and make use of the parallelism of the SGI multiprocessor machines. Okay, let's look at some of the loops that could not be parallelized. So I can select my code to show only the loops that were unparallelizable, and I can sort them based on their performance cost or workload so that I can concentrate my efforts on those loops that will give me the most bang for the buck. Let me pick one of these loops now, and if I double click on it, the information it gives me about the loop down at the bottom of the screen says that the loop was not parallelized because there's an obstacle to parallelization, and in this case it says there's a data dependency due to variable A. If I bring up the source code and I click on that little icon next to the data dependency, it shows me the actual occurrences of the variable A in the source that result in that data dependency. Furthermore, it actually shows me, it asks me a question here. It says, is B a permutation vector? And the reason for that is that if B is indeed a permutation vector, that is an array whose values are all unique, then I will be able to parallelize this loop. So beside this question, there's a menu where it says don't know, and I can assert that this is true, that B is in fact a permutation vector. And if I do that, I can now rerun the analysis to update the program, and what it will do is will add that assertion into the code, rerun the parallelization, and now I will have that loop parallelized, and I will have improved the performance of my code. So what Workshop Pro MPF lets you do is look at your code, find out which parts are being parallelized, what sort of transformations are being done, and it will direct you with questions to say, is this a permutation vector? Are these two variables independent? Is this function parallelizable? And you can answer the questions yes or no, and thereby guide the parallel analyzer to parallelize those parts of your program that it was unable to determine were parallelizable by itself. If you develop code in C++, you'll be interested in the Workshop Pro C++ module. This module includes the Delta C++ native compiler with the smart build capability, a C++ class browser, and the ViewKit set of user interface classes used for developing X and Motif applications. The Workshop Pro C++ class browser is an enhancement to the static analyzer that was part of Workshop. It uses the symbol table information generated by the Delta C++ compiler to show classes, methods, and the relationships between the classes. Let's take a look at some of the information and the queries that you can answer using this C++ browser. Down here on the bottom left of my screen, I'm looking at a particular class in an application, and this class is called ColorView. You look on the left, I have the public, protected, and private methods and instance data of the class available to me. I can scroll up and down through this, and I can hide certain parts of it or reveal them in all their detail. Double-clicking on a particular instance or method will bring me up the source code for that method. On the right, I see the class, the relationships of this class to other classes in the system. For example, I can see the base classes of this class ColorView, or the derived classes that are derived from it. I can also see which classes use this class and if there were any classes that this class used, I would see them as well. This relationship between classes I can view graphically as well as textually. If I switch over to the other view here, on the top right, what I have is a graphical view of the inheritance relationship among the classes in my application, with the current class highlighted. I can switch this view to show me either inheritance, containment, interaction, that is which class calls which other class, or friends relationship between classes. For example, if I switch to interaction, I will get a graph showing which classes call which other classes. If I double click on any class in this hierarchy, the main browser view switches to show me the details of that class. In the class browser, I have a queries menu that has a set of queries. For example, what is declared by this class, defined, overridden by, what instantiates this class, what uses this class to contain as a friend, as a method, as a data member, what is instantiated, destroyed, and what is used by this class. As you see, we have a very comprehensive set of queries. In fact, we claim that if there's a query about the classes or the relationships between classes that you can't answer using this browser, please tell us and we'll add that query to the next release. The other component of the Workshop Pro C++ module is the Delta C++ native compiler with the smart build capability. One of the problems with C++ is that if you change a header file or a class definition, you end up having to recompile a lot of files in your system, even if those files don't really affected by the change that you made. What we've done with the Delta C++ and Smart Build is add some intelligence to the compiler so that it can recognize a change in a header file and tell whether or not a particular file really needs to be recompiled because of that change. This results in a huge speed up in recompilation of your system after you change a header file. And I'll demonstrate that for you now by running a race between the standard AT&T Seafront based compiler and the new Delta C++ with Smart Build. So if we look over here on screen, I have a header file that I'm going to change. I'm going to change this #define new widget 1, and you'll see that as a result of that, what I add in is some new code here. I add several member functions and member data items to a structure. Now typically as a result of this, I would have to recompile just about everything in my application that used this header file. But I'm going to save and quit this, and now I'm going to start up the two compilers in parallel, and you'll see that both of them will recompile the one file that uses those new functions, but the Delta C++ compiler will skip compiling everything else, whereas the regular Cfront will have to compile them, so that the Delta C++ finishes much faster. Okay, I start the two compiles now. On the right is the Cfront, which starts up first, and you'll see they're both compiling the initial file, widget.c++, which is affected by the change that I made. Okay, now you'll see, if you come back to the screen there, you'll see they've both finished compiling widget.c++, but now the one on the left, the Delta C++, is going ahead, and for each file that it tries to compile, it notices that it doesn't really need to compile it, and so it skips through them, as you can see, taking only a couple of seconds for each file. Whereas the regular C compiler on the right is having to actually compile all those files, and so is taking several minutes. When this ends, you'll see the timing of the two compilers, and we'll compare the actual total running times of the two compiles to give you an idea of the speed up you can get by using Smart Build instead of a normal C++ compiler. All right, if you look on the left here, you will see that Smart Build has now finished. It took a total of 1 minute and 38 seconds in real time to finish the complete build. Over on the right, however, the regular C++ is still plodding along. So we'll cut away for a little while and come back when that finishes and show you the actual time that it took to compile the same build with the same change in the header file. Okay, the Cfront compiler has now finished, so we can take a look at the bottom line results. Over on the left, we see that the Smart Build, by skipping the compilation of the files that didn't actually need to be changed, even though they appeared to need recompilation, managed to do the full compilation and rebuild of the system in 1 minute and 38 seconds. Over on the right, though, we see that the regular compiler, by having to compile all the files as a result of the header file change, required a total of 5 minutes and 25 seconds. So this is a really useful speed up and lets you finish your compiles and builds much faster, thereby really easing the burden of C++ development, as we found out here by using Smart Build in our C++ development. The final piece of the Workshop Pro C++ module is the ViewKit user interface component set. Now, I'm not demonstrating this because it's basically a set of class libraries that you can use to build X and motif applications, but you have seen it. All of the tools you've seen here, the graphical components of them were built using the ViewKit. So you've seen how they work. Some of the pieces you get with this are color schemes. You've seen the color schemes here of all the tools. There's an integrated help subsystem, tool talk messaging between applications, and basically a lot of the X and motif boilerplate that you have to do in order to write applications in X and motif is taken care of for you automatically by the ViewKit user interface class set.
Good morning, my name is Mark Hughes and I'm the product manager for Tracker. Tracker is one of the CASEVision range of products for software development. And I'm going to explain to you now and give you a demonstration on how Tracker works. A major problem in software development is tracking quantities of data. This problem is not restricted solely to software development, but in any organization there is always a need to track data, especially through state changes. If you can imagine things like bugs with a bug tracking system, you have a set of data which needs to be tracked through a number of state changes as the bug changes state. Tracker is a tool which allows you to design applications to provide communication with a database to track this data through a number of state changes. As you can see, these applications are going to provide the user with an X window motif interface into a database, a context-sensitive help subsystem for help on the application, checks for valid data entry so people cannot enter the wrong type of data into the database, and communication with the Unix operating system so that actions can be carried out on state transitions to inform people about changes in data. There is also security on the fields which can be changed. Tracker is an application which allows you to build other applications. However, as part of Tracker, we do ship a full-blown bug tracking system which we developed ourselves here at SGI. What you would probably want to do with a bug tracking system like this is modify it for your own use. You can also design your own applications to track other sets of data. Some of the things we use Tracker for here at SGI, for example, is call tracking to track customer calls, to track calls from sales reps asking for information, the status of our evaluation software we may send to customers, and tracking beta sites. The uses for Tracker are really infinite. When you have a database with data stored in it, there are a number of ways of accessing that data. We provide a language called DML, Data Manipulation Language, which is an SQL-type language which allows you to access this data. Another way to access the data is through an X window motif interface. And what I want to explain is why you need the two different ways to access the data. The DML is really for administrators only. You have to write in an SQL-type language, and it's very easy with DML to access the database and enter the wrong types of data. The X window user interface is basically an interface between the user and a database which only allows them to enter certain data. It checks for valid data types and restricts what the users can do to the database. It also makes it much easier for non-technical people to communicate with the database. If you're going to design a Tracker application, where do you start? Well, firstly, you probably start off with some sort of state transition diagram which models the process that you're trying to track. So basically, here is a simple bug tracking system. If you submit a bug, it goes into some state which I've called a waiting response. If you resolve that bug, then the data transitions to a state called closed. You can reopen the bug or assign the bug. Secondly, once you have this design, you enter everything about the design into a file called a PDL, or Process Description Language file. This file contains 3 sections. Firstly, you define the field names and the types and values that they can have. This is the information that will be stored in the database. Secondly, you design the state transitions that can be carried out on this data. And thirdly, you define the views or the layout of the graphical user interface that you want generated for you. Here's some examples of the different sections in a PDL file. Firstly, we have the field section. And here are some fields that you typically have in a database for bug tracking. You have the priority of the bug, a project that the bug is reported on, the close date of the bug, a summary, a description, a submitter, and a notify. These are all fields that are defined solely by the user. And you can see the simple data types, short text, long text, dates, one-ofs, that you have available to choose from for this data. Secondly, you want to design the transitions that this data can move through. So here are some simple transitions for a bug tracking system. We have one transition called submit bug. So when you first find a bug, it has no state. Submitting it takes it to awaiting response. When you resolve the bug, the data moves from the awaiting response state to a closed state. Associated with each transition are rules and actions. Rules have to be carried out before a transition can happen. So for submitting bug, the rule is that the description is set. So the user has to at least put in a description of the bug before he can transition that data to awaiting response. Once the transition is completed, actions are carried out, and here we're saying that we're going to set the value of the submitter to the environment variable $user. In other words, the person who's logged in and using the system. When we resolve the bug, we have to change the description, and the system will then enter the close date to be the current value of the date. The final part of a PDL file is the views section. And here, this is just the layout of the graphical user interface. So you define where you want the fields to appear in your graphical user interface. You also define the transitions that are available in a pull-down menu, because you may want to restrict the transitions that a user can actually access. So that's a quick overview of Tracker and how it works. Now let's look at a quick demonstration just to show you how easy it is to design a Tracker application. And the real key to Tracker is the ease with which you can design applications. So here we have a typical PDL file on the left, just showing some text in a PDL file. And I'm going to show you how you can compile this PDL file into a real application. So we have a fields part, a transitions part, and a views part to this PDL file. There's also some help in this PDL file as well, and I'll show you how the help is compiled into an online help subsystem so you can provide help on any application for your users to any application you may design yourself. So the first step is to take this PDL file and run a compiler on it to generate an application. So here we're just executing a Tracker program called tvgen, which creates a database for you if there isn't one there already, and populates that database with the contents of the PDL file. This only takes a few seconds. It's also generating the X-Window application. tvgen has finished. Secondly, we run an install procedure to install our application. This basically creates some links into standard Unix places. This is also very quick. And thirdly, we want to run the application. So all we're going to do now is bring up the X-Window motif interface into a database that we've just created. And we're going to do some work with the application. As part of the demonstration, I've actually populated this database with a couple of bugs, so you can see what a database would normally look like. And here we have 4 bugs in the database awaiting response. So this X-Window application, the layout of it was defined by the views part of the PDL file. I can query the database by querying here. I can basically do things like submit bug by looking at this pull-down menu here and choosing submit. When I choose submit, you'll notice the description part of this interface is surrounded by a red border. This is because the description is a rule and is mandatory. I must fill in at least a description of the bug before I'm allowed to submit it. The submit button up here is not highlighted until I enter a description. So let's just type something in and say, there's a bug in CV speed, dumps core when the X option is selected. Now I've put in a description, I'm allowed to hit the submit button. What happens then is the date and the submitter are entered for me because that was part of the PDL file, and the bug changes state to awaiting response, which is its first state. It also has a unique number associated with it. It would be easy to enter some other bug just by once again clicking on submit and entering a description. Once I have bugs in the database, I can query the database by example. So if I go to query mode, clear the database, I can say, show me all the bugs that are awaiting response. And there's a number of them, 6 in fact. If I want to resolve any of these bugs, I first bring up the bug, go to resolve in the pull-down menu. The rule is that the description's got to be changed, so I enter some resolution for that bug. The bug now changes state to closed. So once again, I could query the database and say, show me all the bugs that are closed. And there's only the one that I just closed off. This is just a simple example. Tracker applications can be much more complex than this and much more powerful. But I just want to show you how easy it is to design an application. If I wish to now modify this application and make it more powerful, I want to exit the application. I'll edit the PDL file. So here we bring up an editor, look at the real PDL file. Maybe I want to add a new priority value here. I have low, medium, or high. I'm going to add in critical. I save and quit out of the editor, and once again run the compiler. It saves the previous version and adds the new information into the database. We can modify this database while it's active and running. Once that's happened, I don't need to do the install step again. I've already done that once. I just run the application. So once again, it's going to bring up the X window interface, and we should see my changes in there. It's very easy to rapid prototype with Tracker. You can get something working very quickly and then modify it. So if we look at the priority field, we now have 4 values, low, medium, high, and my new value, critical. So I can ask, for example, to see all the bugs on the Tracker project that are awaiting response in critical state. And of course, there are none at the moment. I also have help. If we go to the top right, there's a help on context menu item. I get a question mark. If I click, for example, on the priority field, it'll start a help server and show me any help that I've designed into the application associated with the priority field. And there's the help. I can bring up a help browser and see hierarchical help. So I have 3 levels of help in this particular application. By clicking on them, I see the help associated with each level. So just by writing help text into the PDL file, I can have it compiled into this online help subsystem, so any users of my Tracker applications can access context-sensitive help. So that's a very brief overview of Tracker. As I said, it's not restricted to bug tracking. You can basically design applications to track any sort of data using Tracker. And at SGI, we probably have around a dozen different uses for Tracker, and the number of uses for it are growing every week as people begin to understand the power of Tracker. Starting with a commercial database and designing an application like this is very time-consuming and expensive. If you purchase Tracker, you can design any number of applications and duplicate the database any number of times. Hello, Mark Hughes here again to talk to you about one of my other products, ClearCase. ClearCase is a configuration management product for tracking software changes. I'm going to explain to you, with the help of a few slides, some of the concepts behind ClearCase. And then there'll be a technical demonstration showing you how ClearCase works on a software development project. A little bit of the history of ClearCase. Many years ago, there was a product called DSEE, Domain Software Engineering Environment, or DISY, as it was affectionately known, that came from Apollo. When Hewlett-Packard merged with Apollo, the main designers of the DISY product left and formed their own company. Dizzy was extremely successful, sold 30,000 licenses worldwide, and was way ahead of its competition in software configuration management. Well, this new company was called Atria, and ClearCase is their first product. It's basically a Unix version of Dizzy, greatly enhanced, running on many different workstations. The beauty of ClearCase is that it allows you to rebuild, recreate, and work on old versions of your software. It's not necessarily restricted to software. You can configuration manage any Unix file system object using ClearCase. So it's used for hardware design, for tracking documents, as well as software. Okay, let's look at some of the slides and explain some of the concepts. Software configuration is probably the biggest single headache in software development today, because when you're producing many versions of software that run on many different platforms, then you have to track all of these different versions somewhere on your system. People do it very badly usually. ClearCase is specifically designed so that you can develop multiple versions of software on multiple platforms and track everything associated with those versions. That's not necessarily just the source code, but also libraries, executables, subsystems, documentation, data flow diagrams and structure charts, test programs, test data, even the project directory structure, which changes over time. These are the sorts of things that ClearCase can be used to manage. ClearCase is really a set of tools. It's a tool set for configuration management. The main tool, which we'll see in detail in the demonstration, is called ClearTool. This allows you access to most of the ClearCase functionality. There are some other tools, one called ClearMake for building software systems, one called ClearMerge for merging different versions of files, and another one called ClearVtree, which gives you a version tree graphically, so you can see how your software has evolved over time. Don't switch off now just because this is a technical slide. This really explains the concept of ClearCase. Anything that you're storing under configuration management is stored in a database that we call a VOB, or a versioned object base. There can be one or many of these versioned object bases, and these can be scattered around your network, residing on file servers. Any Unix workstation basically can hold a VOB as long as that workstation is running ClearCase. What you then do is mount this VOB on your file system so that users can see versions of files within this VOB. What you want to be able to do is select the versions of each file that the users can see. And this is done through the view. It's a view into the database. The view is a concept. And basically, it's a filter, so different versions of source code are projected into the Unix file system. The versions defined by the view are defined by a set of rules called a configuration specification. So here we're basically saying that we want to see in the Unix file system versions of elements of things under configuration management, versions of elements that we have checked out, or the latest on the main line. So this is a development view where we're working with the latest versions of files. These files are then projected into the Unix file space. By changing that set of rules, I can, for example, say, show me everything that went into release 1 of my product from 2 years ago. And in the Unix file system, I will then see the particular versions of each file that went into producing release 1 of my product from 2 years ago, instantly in the file system. The key is that nothing is copied from the database. It's a projection of the appropriate versions from the database into Unix file space. We call this transparent versioning, and it comes about through a new file system built into the kernel called the multi-version file system. This is the real key to ClearCase. The features and benefits that you get from ClearCase are, firstly, as I explained, full version control of versioned objects. So you have instant access to any version of any file that went into building a system, and you have an audit trail over who made the changes, why, when, where, which machine they were working on, what operating system the machine was running, all the sorts of information you need to know when you rebuild a system. The transparent access to versioned objects means that applications can work with those objects. You go back to release 1 of your product, All of your Unix utilities, your frame maker documents are accessible through Frame. Everything is accessible through standard Unix tools because you're basically looking at Unix files, even though they are really projections from a database. This is the version control aspect of ClearCase. The other aspect to it is configuration management or build management. And what this really means is keeping track of configurations of software, what went into building releases of your product or different versions of your product. And basically, we need to know everything about building a release, not just the source code that went into it, but everything else, the make files that we used, the versions of the tools such as the compilers, the test data associated with those versions, the documentation. Everything can be recreated instantly and logically through ClearCase. Parallel development through branching and configuration specs means that more than one person can work on the same file at the same time. One person can be working on doing development on the latest version of a product. Another person can be fixing bugs in a previous release. They can work on the same files at the same time without interfering with each other. Binary sharing means that when developers produce binaries, then those binaries are unique. If a developer tries to build a binary that's already been built by somebody else somewhere on the network, ClearCase will find that binary and create a link to it. So the only binaries you ever produce are ones that are unique to yourself. This binary sharing means that not much has to be rebuilt. When you do a recompile, most binaries will be shared because they've already been built by somebody else. And finally, parallel heterogeneous building means that you can build in parallel on a heterogeneous network. I can say to the system, go away and build the latest version for Sun. I give it a list of Sun machines available on the network in a file somewhere, and it goes away and farms out the compiles around the network on the Suns and gathers back the results, gathers back the derived objects produced by those compiles. I don't need to copy source around the network. It's all done through NFS. You can also build easily on computers that don't run ClearCase. For example, a Cray or a Convex may never run ClearCase, but there's no reason why you can't build the Cray version of your software easily as long as NFS is accessible. Once again, you don't have to copy source. If you don't have NFS, you may have to copy source, but this isn't normally the case. This slide just illustrates binary sharing. As I said, most binaries that are built by a developer are shared by somebody else. And only the unique binaries that are not shared by anybody else appear in the developer's view. Everything else is stored in the database and shared. So basically, with ClearCase, we do have, with the other CaseVision tools, a true integrated environment. ClearCase, Tracker, and Workshop are all integrated together to provide tools to cover the whole software development life cycle from start to finish, from the moment you start coding to the final stages of testing and releasing software. Silicon Graphics have case tools to cover this. So now, to explain some of the concepts in ClearCase and show you how it works in real life, I'm going to call on my able assistant, Anil Pal, to demonstrate ClearCase for you. Thank you.
Hello. I'm going to take you through a typical development session to show you how ClearCase and Tracker can be integrated together to let you develop and maintain software. What I'm going to do is be working in a development view, developing a piece of software, when I receive a bug report against an earlier release of the software. Using ClearCase and Tracker, I will then go back to that earlier release, fix the bug in that release, make a new release of the software incorporating that bug fix, and then merge that bug fix into my current development. So if we take a look at the screen over here, on the bottom left of the screen, I have the history of a particular file that I'm working on. There is the main development branch of the file, which has versions 0, 1, 2, 3, and 4. Version 2 was the version used in release 1 of the software. Subsequent to that release, I made some fixes to this file, and those go on a branch called Release 1 Fixes, where I have versions 0 and 1. Version 1 on that Release 1 Fixes branch was then merged back into the main line to create version 3, and I've since done some more development on this file to create version 4. Okay, now we'll switch over to my working window here, where I'm going to be doing some work on this file. First, let me do a simple ls, which shows you the files that I'm working on in this directory. All of these files are stored under ClearCase, and so you'll see that they are read-only, but they are in other respects just like regular Unix files. Which versions of the file I see is governed by the ClearCase view that I'm working in, and the command cleartool print working view, or PWV, tells me which view I'm looking at. In this case, I'm looking at my devel view, which is what I use to do development. Part of the view is something called the configuration specification, and by looking at this configuration specification, you'll see I have rules saying I want to see the checked out version of a file first, and if I don't have the file checked out, I want to see the latest version on the main branch. Okay, so what does that mean for my current development view? If I do a cleartool ls, that shows me which versions of file I'm looking at. So for example, for jack.c++, you'll see I'm looking at the version at is the version extended naming. So it says I'm looking at jack.c++ version 4 on the main branch, and this is determined by the rule main latest that I had in my configuration spec, and it's the same for all the other files. Okay, for an individual file, I can get more detail on the history of that file using the command cleartool ls history. In this case, it will show me for jack.c++ who created which version, when it was created, and any comments that were provided at the time the version was created. I can refer to any other version of a file at any time by using the version extended naming. So here I can difference the current version of jack.c++ that I'm looking at with the version that was used in release 1 based on the label I put. So this is going to bring up a side-by-side difference between the two files, where each of the changes is highlighted in color, showing me what I have changed in this file since release 1. Okay, back to work. First thing I probably do with the software is to build it. Now in this case, since someone has already built these versions of the files and I don't have them checked out, you'll see that it doesn't actually build anything, but rather simply winks in or creates a link to the existing versions that have been built by someone else. And now that I've winked them in, you'll see I have the derived objects existing in my view, and they were created by some other user. Let me run the program now that I've built it so that you can see what the program looks like in its current state of development. It's an inventor application with a jack-in-the-box with a little spherical head with a smiley face texture mapped onto it. Okay, let me go back now. I'll move this out of the way and go back to working on my current development. And what I'm going to do is check out a file and work with that file. So the jack.c++ file, I will say check out, and it checks out that version from main 4. And if you look down on the left at our little version tree again, you'll see this now indicates that we have a reserved checkout in my current view of that file. All right, so once I've checked out the file, I notice while I'm working on it that I get a bug report comes in. So I may have got mail or somehow some indication has been sent to me that I've received a bug. So what I'll do is I'll bring up Tracker and then take a look using Tracker's query mechanisms to find all the bugs assigned to me that I need to work on. And here I bring up Tracker, and it automatically does a query that I've saved away to show me the files that are mine, the bugs that are assigned to me. So I have one bug that's awaiting response. It's owned by me, case demo, and there's the summary of the bug showing in release 1 the jack-in-the-box is not smiling, and this must be fixed at once for an important customer. So now I know that I need to go back to release 1 and fix this bug in the program. So let me do that now. What I'm going to do is create a new view to work in where I will look at the versions of the files that went into release 1 and make the bug fix there. So let me do that. So I'm creating a view here with the tag maintenance that I'm going to do my maintenance work in. So it's created that view for me, and it's owned by me. And I'm now going to set the configuration spec for that view and change into that view so that I look at different versions of the file. So you see now, instead of the devel view, I'm in a maint working view. Now what's different about this view? Well, it's the configuration specification. Those rules are referred to earlier. In this case, the rules say, if I have a checked out file, that's what I want to look at. Otherwise, I want to look at the latest version on the release 1 fixes branch, because I'm making fixes in release 1. So I want to look at the latest version on the fixes branch if there is one. If not, I want to look at the version that went into release 1 if there are no fixes. And also, if I check out that file, I want to automatically create a branch called release 1 fixes in order to put that checkout on. So if we come down here to the left again and look at my version history tree, what I'm saying is I want to look at this version here on the release 1 fixes branch, the latest version, if that exists. If not, I would look at the actual release 1 version and create a branch when I check it out. Okay, so let's get back to work then. And what I'm going to do now is list the files that I look at with this configuration spec. And you'll see that I have a much reduced set of files. The product was much simpler in release 1. There's only a few files, there's no derived objects, and they're all read-only once again. So let me list which versions of the files I'm looking at now. And these are the release 1 version of most of the files. Okay, so let me build the product for version 1 to verify that the bug does indeed exist. So, and once again, you'll notice that since someone else has probably been working on release 1, that it's actually winked in everything rather than actually building them. So now let me run the release 1 version of the product, and I'll bring this up now, and you'll see that it's different from the release 2 version, in that here the jack's head is a cube rather than a sphere. And we see that the bug is indeed true. The jack is not smiling. Okay, let's quit out of that, and now we'll work to fix that bug. Okay, so what I'm going to do is I'm going to check out the file, jack.c++, but now we see the integration with Tracker. Since this file I'm going to be checking out on a bug fix branch, what it does is it asks me which bug am I fixing. Okay, so let me first enter a bug number which is invalid, and it's going to check that with Tracker, and it's going to determine that the bug is not in the correct state awaiting response for me to work with, and so it refuses to allow me to check out that file without a valid bug number. Okay, let me go back and check it out again, and this time I will give it the actual bug number that I'm going to be fixing, bug number 3. So it will now check out the file for me and tag it with work in process that I'm working on bug 3 on that file. Okay. I now will run through and make the actual fixes to that file, and for the purposes of this demonstration, we'll assume that's being done trivially. As part of this, I'm going to check out and fix some other files as well. So we'll write the bug numbers in there for those files. When I check in the files after I make a fix, it confirms with me that I have in fact fixed the bug number that I said I was going to fix. Okay, so it will prompt me again with the bug number I gave when I checked out the file and ask if that is the bug number that I'm going to fix. So let me build the file now that I've done this, and it will actually compile this time. Note that it says that the version for jack.c++ has changed, so it does have to build a new version of it. It will build that, it will link it into the final product, and then we can look and test to see that the bug has actually been fixed. Okay, once it's built, we'll run the new product and verify that we have actually fixed the bug. So we bring up the new Jack, and we see now that he is in fact smiling as was required by the bug fix. So now that we have that, what are we going to do? Well, we check in the file, and once again it prompts me to say, is this the bug number that you fixed? And it is in fact bug number 3, so I fixed that. It will at this point communicate with the tracker database and tell it that this file was changed to fix this bug, so that later I can use that information in the tracker database. When I go to make a release, it will know which files were changed and which bugs were fixed by those changes. Okay? So now that I've verified that I fixed the bug, I'm going to actually make a release of this product. So I create a release called release 1.1. It's going to create a label called release 1.1 and put that on all the files that were used in this release. Then, based on the versions of the files that were changed, it will query tracker and find out which bugs those changes fixed. Now, since I used the latest version on the release 1 fixes branch, I automatically picked up the bug fix for release 1. So the list of bugs that are fixed in release 1.1 is bug 1 and bug 3. And they're both fixed, and it gives me a nice little summary of the fixes that are gone into this release. And if we come down to the left and look at the history of the file again, we'll see that the release 1.1 label has been put on this new file that I've checked in version 2. Okay, the final piece remaining now is that I've made the release, I've labeled it so I can recreate it, and I've got a list of all the bugs it's fixed. The one thing remaining for me to do is to make sure that this bug doesn't recur in the current version of the software. And if you remember, when we looked at that version of Jack, it did actually have a frowning face and not a smiling face. So what I need to do is to take the change that I've made to fix this bug and merge that change back into my mainline development that I used. So I'm going to do that now. I'm going to go back to my development view and merge in this change that I've just made. So I'm back in the development view, and you can see I print the view to verify that. I'm in the development view. And now what I'm going to do is I'm going to use the ClearTool XMerge command, which brings up a graphical merge. And I'm saying I'm going to merge into jack.c++ the latest version on the release 1 fixes branch. So when I do this, it's going to refer back to the history tree and find the common ancestor of the file. So I now have the fixes I just made, the current development version of the file, and the common ancestor. And what it does is it will step me through the changes one by one. It can do this automatically, but in general, if you don't trust it, you can step through the changes. So it highlights the change for me, showing that I deleted this line, and asks me if I want to accept this change. And I say yes, then shows me the next change that I've made in the current development version. I can accept that. And now we come to the actual change that I made to fix the bug, where it changes the file smile.rgb so that it gives me the correct file. And of course I want to accept that change because that's the important bug fix. And I say yes to accept all the other current development changes that I've made. When it's finished, I can save that to a file. And it has now, if you look at the version history of the file down here on the left, you'll see that it has recorded the merge with an arrow in the version history tree of the file. There's this little arrow showing the merge from the release 1.1 into the checkout that I have here. All right, now that I've merged the bug fix back into the mainline version of the program, what I'm going to do is build the mainline and verify that the bug is actually fixed in the mainline version of the program as well. So what I do is I type in a clear make for this version of the program, and that builds jack.o since I've now changed it to merge in this change, and then it links the final piece together. And when that's done, I can run the Jack program again, and this time you'll see that the new version of the program with the spherical head comes up with the smiley face. And so I have in fact fixed this bug in both the old release and the new release. So now that I've done that, I can check in this new version of jack.c on the main line. And that's the end of the bug fix. And that's all I need to do for this. One final thing I'll show you is the integration with Tracker, which we've sort of been seeing all along, where ClearCase communicated with Tracker to find out which bug I was fixing. But at the same time, when I checked in the files, it was notifying Tracker that I had changed this file in order to fix that bug. So if I now go back to my Tracker application, and I look at this bug number 3, which was assigned to me, I can bring up an auxiliary view which gives me the list of files that were changed for this bug fix, and it should show me the list of files that were changed for this bug fix. And you'll see here it does have a list of files and their versions that were changed in order to fix this bug. So this gives us the integration between ClearCase and Tracker in two ways. One is when I'm using ClearCase, it queries Tracker to ask for which bugs I'm fixing and checks that they are valid bugs. And when I check in files, it notifies Tracker to give it the list of files that I've changed, so that when I made the release, as you saw, it could give me the list of which bugs were fixed and which files were changed for that.